Um, I will start by making a big excuse to all the audience. I don't have an AI slide. I will just talk about time and frequency. Most recently, we are developing a coherent time and frequency transfer transceiver. The reason for that is a change in network design from amplitude modulation to coherent networks. Time and frequency community haven't changed their equipment to coherent stuff yet, but we are aiming for changing that. This is an outline of my speech. I will tell you a little bit why we do time and frequency transfer in Sweden. I will give you a brief overview of the natural distribution. I will give you some background introduction as well as specification for what we are doing. The system so far, and then we might have time for some questions. So, why do we have a national distribution system for time and frequency? Citizens are reliable as well as critical public services are dependent on electronic communication. Electronic communications are dependent on time and frequency as well as synchronization. Normally, and due to the fact that GNSS are kind of cheap to buy, they are reliant on GNSS. But the political climate has changed, and we can't use GNSS in the same manner we used to do. So, what is built in Sweden? We have an independent system that is independent on GNSS. It should be robust, and it should distribute reliable time and secure time. Also, it should be working in the whole of Sweden. And also, the regulatory authorities must be given transparency and also have access to the system. We have this kind of nodes in Sweden. So just to give you an overview, in the bottom we have cesiums, not the ones that you were previously shown. We also have the frequency and phase adjustments. That is only just microsteppers. We have amplifiers. We do frequency measurements, distributions. We're able to distribute PDP and NTP and so on, as well as we have management for the network, also web service to be able to present what we are doing. I will later on show you where we have these sites and how it's implemented in the system. So the Swedish model then is funded by Post and Telecom Authority. Netnod is the one that is distributing the Swedish time. We also have traceability to the national timescale, hosted by RISE, Research Institute of Sweden. We have 6 time nodes, and they are redundant. They are placed at 5 locations across Sweden, from Luleå up in north to Malmö down in the south. We have different kind of services, like the free ones and also the ones that cost a bit. So once again, the same slide. In this case, we stated which kind of clocks we're using as for the moment. One of the main drive of these systems are our NTP and NTS servers that were custom built to not be DDoSed. And then we need to talk about the services we are providing. So we provide NTP and P2P. We have time direct. P2P is the most accurate one in a nanosecond. Then we have Netnod time direct. It's an X service, about 30 microseconds in accuracy. And then we have Netnod time remote. And the accuracy is about 1 millisecond. The free services are the NTP services. And then, you know, everyone is in millisecond range. And then we have the NTS service. I will stop by the NTS service due to the fact that we also have these at all 5 locations. So please look at those. That is the secure. It's encrypted, and you will be sure that you get the right time. So now I will come to the fun part. Everyone is talking about clocks. I wouldn't say that we are talking about clocks, we are talking about oscillators. It's only clock when you set the starting point and then count happenings after that. So in the timing community, we see these kind of graphs that you can see to the left. There are different kind of clocks. Normally we use, for many systems, use these GPS disciplined oscillators. As you can see, they are not that good. And on the y-axis, we have the stability. On the x-axis, we have the average in time. So as longer average in time will give you greater stability. The clocks we are using are here presented in purple, the HP 5071s. We are not using the high performance, but they are more or less the same for a week or so. And the best commercial clocks that are able to buy are hydrogen masers, basically a laser before it lasing. As you can see, we can reach down to a couple of parts 10 to minus 15 in stability. In our case, for the cesiums, a couple of parts 10 to the minus 13 in stability. But okay, so it's good to have good clocks. What could we do with those if we can't compare them to each other? So we need to have different kind of dissemination systems. So we have the satellite ones up in red, and as you can see, to be able to compare maser, we need to have a really long average in time. For cesiums, it might be working. That's the reason for using White Rabbit or precision time protocol. As you can see, in between 10 and 100 seconds, you are able to compare masers against each other. So now we have some oscillators, we have dissemination methods. We also need to have a real source for timing, a national one. And this is a Swedish national time scale. I think the next presentation will give you more input about that. I will just give you a brief overview. So they have several clocks. They create a group clock by comparing them to each other. They apply a correction, and then they will have the national time scale. That time scale is then compared to other countries by GNSS and also by two-way satellite time and frequency transfers. The results come back, and they use it to apply the correction and also send the data to Paris and Bureau for data handling in Paris anyway. So why do I talk about the national time scale? Just to give you an overview of what we are doing. We take the time from a national time scale. We get traceability to our sources on our nodes. Then we are distributing it to the society, highest up, to positioning, aviation, defense, EU projects, HPC, research, energy sector, and also to authorities. So is anyone here reliable or reliant on time? I think so. Every one of us is that. So I started this presentation by telling that we have seen a change in network. So about a year ago, or maybe more, we used SUNET, the Coherent network, to send amplitude modulating time and frequency in duplex fibers to just see how it's working. We used a distance between Gothenburg, or more or less Onsala and Borås, 80 kilometers. It's a round trip time of about 8 milliseconds. And we wanted to see how good could it be. The round trip changed about a couple of hundred nanoseconds, so it's working, but it's not working good enough. And also, we could have one or two of these connections. We can't have several due to that we will break the coherent network. So what are we planning to do then and now? So I went back and talked to one of the guys at Chalmers and also Mikael Masur at Nokia. They already had a project together with Sunet. What they were performing was using fiber as a sensor. Really impressive work. And I thought, okay, so if they are able to use a fiber as a sensor, can I compensate for that? Then I can do a time and frequency transfer. So I took some slides and got them from Mikael and Chalmers. And also I have Erik Börjesson in my new project. So what they did, they used fibers as a sensor. And some examples of effects or techniques they're using is phase interferometry, polarization interferometry, Rayleigh and Breno and Raman scattering. So why do they don't just lay out their own fibers? Too expensive. We already have a lot of telecom fibers, so that's not an issue. And also, it could help the telecom fibers to be more reliable. Some other examples from their presentation. They use state of polarization to track earthquakes. You can see the state of polarization up to the left during an earthquake and afterwards. So really, really good sensor. So there weren't any coherent transceivers for these kind of experiments or measurements. So they used an FPGA, created a coherent DSP engine. They used 1 gigabaud transmission, just 125 megahertz clock and 8 parallel channels inside it. The sensing capabilities were polarization and phase sensing. Also, they used hardware and software filters. This is kind of bulky, and some parts of this solution is obsolete, so we can't use that for the coherent transceiver that I'm proposing. They took it to Sunet and performed a test in a live network. They connected it in Gothenburg, went up to Karlstad, and back. They don't have any passive filters in this. They just drop out all the wavelengths, do a passive splitter, and then they do coherent homodyne configuration and detection of it. So this is the distance they're using. It's one way, 262 kilometers. That passes 5 ROADMs. Yeah, and it's in Sunet. Also, the fibers are hanging along the power grid. Due to that the fibers are in the air, they could measure the temperature along the way. And in the bottom graph here, you can see relative delay in nanoseconds in blue, and in red, you can see the outside temperature along the path. So it's a temperature sensor. Very expensive, but still temperature sensor. Yeah. Also, they have a strong 50 hertz tone in all the measurements due to Faraday effects of the fiber. It would be really interesting to use this along the railway and see if we could track the trains instead. We also know that we could see the wind. As you can see here, we have a minimum wind, we have a maximum wind, and we do it by measuring the state of polarization. So far have I only talked about what is done. Now I will give you an idea what we are going to do and what we have done so far regarding a coherent time and frequency transceiver. We have some collaboration partners. We have RISE, we have Erik Börjesson at Chalmers, we have Synective Labs, Netnod also, and our funding partner is Post and Telecom Authority. So we proposed this project, and we wanted to figure out which kind of limitations do we have. We can have no or very, very small amplitude variations. Also, we know that the network can handle 100 gig dispersion. We might not send 100 gig, might be less. We need to be able to cope with duplex transmission. And also, we know that 50 Hertz polarization variation will be hard for us. Limitations from a time transfer system will be that we need to combine 1 PPS with timing data on the same channel. We need to figure out how to compensate for asymmetries, both statical ones and the dynamic ones. And also, our equipment must have a constant delay within it. Otherwise, we can't cope with asymmetries. And also, the output from the system need to be able to be adjusted for, so we could move the timing out from our boxes. We call the system TIFCON. It consists of 2 identical boxes. We need to have frequency into it to be able to transfer it, to distribute it. We're looking into have 5 to 1,000 megahertz. And the ADEV, the average in time, should be, and stability of the system should be better than 1 part 10 to minus 13 at 1 second. That is better than our cesium clocks. And below 1 part 10 to minus 17 for 1,000 seconds. We should be able to cope with 1 PPS or 100 PPS. 1 part per second or 100 parts per second. Also, the time deviation of that should be better than 3 picoseconds for 10 seconds average in time. And better than 1 picosecond at 1,000 seconds average in time. We should also be able to stabilize against the variations, fixed or induced, and do phase correction interval. We should have a phase correction interval of about 2 microseconds. We should be able to adjust the outcome in 1 PPS. And when I talk about 1 PPS, that's how we state the time, somewhere in the flank of the 1 PPS. We should have a maximum optical loss about 25 dB. Some more specifications. We should be able to have active delay stabilization. Auto calibration. It's really, really hard to do. Normally, we state that both paths are equal and divide by 2. We can't do that, so we need to have another way of measuring the distance. So we have some ideas about that. We need to have PPS adjustment. I talked about that previously. Also, the dispersion option. We know that we need to handle that, dependent on which kind of data rate or rate we are using. So this is one of the first schematics of systems. We have the electrical interfaces, 1 PPS, frequency, PTP, NTP, and whatever. We're looking to have 4 inputs. We need to be able to actually select which kind of wavelength we are using. The output should be between 10 and 100 gig. We should be able to actually work it in BID also. We will have output of the system, 1 PPS, and the frequency. Also, it needs to be able to be daisy chained if we have several connections. One early sketch of what we would like to do. We will have the DSP, we have an RX input, we have a polarization beam splitters, we have the hybrids, and we will have 8 inputs to the photo detectors. We will handle the data, keep track of polarization, and so on, and then we will have timing data, frequency, PPS, and whatever timing protocol we would like out of it. We will have an IQ modulator, and we will have a more stable laser than they are using in telecom systems. Most important is that we will have a constant delay of the transmitter as well as the receiver, and constant, nothing is really constant, which means that we can have a jitter, and that jitter must be less than plus minus 50 picoseconds. For our initial test or proof of concept, we looked into quantifies already existing front end. So this is a transmitter part we are looking into using before we make a final equipment. It's easy, it's already there and can handle whatever we like. They also have a receiver that we could use, and then we can focus on the FPGA and DSP in the back. So here you can see the PBSs, the hybrids, and the detectors and so on. So a bit of poor build or poor picture. Just to give you an idea, we'll have optical inputs, we will have the ADCs, we will convert it to IP, timestamp it, and do some digital working and do it constant in delay, and then we will have the output. So we are in the progress of producing these the codes for the FPGAs and the platforms. So this is just an initial schematics of it. So far, we have a consortium. We figured out what to do. We think we have the hardware for it. These are the specifications we're aiming for. It's QPSK or 16 QAMs. We would for 10 or 100 gig. I think we will probably settle for 10 gig. It needs to handle 1 PPS. The frequency will be in between 5 and 10 megahertz. 5 megahertz is a common frequency for NMIs. That's the reason for using that. It should fit in a 19-inch rack. We should be able to use BiD or duplex fibers. It should be able to transmit or compare clocks in sub-nanosecond range. We should be able to cope with precision time protocol or White Rabbit, which is a profile of PTP. It should have redundant power. We'll base it on an FPGA. It should be daisy chained. We should be able to select the wavelength, and also we will be able to actually have the optical ref as an output to measure on it. So what we'll do when we have the equipment done. One idea, what we are proposing, is to do this it's an initial start of a Nordic timing network. They do a lot of timing networks in Southern Europe, but I think we can do it in the northern part. And then we have the NMIs, not all the NMIs. We are DFM in Denmark are progressing, so they will be there later on. But we have the fiber routes between JV in Norway, also to RISE in Borås, and RISE other sites up here in Stockholm, as well as we have the connections to Mikes in Finland. That would be really, really interesting. Seems like we have time for some questions.
Yeah. Are there any questions for Svenne? We got a question right at the back, just on the left there.
You mentioned that you were measuring the 50 hertz. I'm guessing that's from the mains hum, from the frequency of the mains electricity.
Yeah.
Do you do anything with that? Because I know in the UK, the National Grid records it, and we then use it for verifying recordings in criminal cases and things like that. Do you have any secondary uses with your very precise monitoring of 50 hertz?
Not so far. It might be in the future, and I don't really know what the power grid guys are doing. They are already monitoring it, but we do it better. I don't really think they need our precision, but I don't know if they're doing anything with it.
Any more questions? We've got two on Menti.
So first question, why 100G in TIFCON or even 10G? Isn't it better to have a design with separate front end to handle bandwidth demands? Will timing be better with 100G?
Yeah, it will also be more expensive, and we will have dispersion problems. So you should keep in mind that we are not talking about data transmission. So it might be better to have lower bitrate as well as sending 1 PPS. So we will be sending 1 PPS, and then I think we will figure out a way to introduce a lot of other bits, dummy bits.
So this question might be directed to the previous speaker, but I think you can answer it. Who decides GPS time, and is that the canonical time?
GPS time. This GPS time is steered by USNO, US Naval Observatory in the US. So it's actually military time, more or less, since USNO are steering it and they control it and do everything about it. And they have roughly 200 clocks, I think, to steer it in some kind of way.
We have a question just here.
Hi, when will ntp.se start working again?
That's a really good question I can't answer.
Okay. Well, thank you. Please join me in thanking Svenne for a fantastic presentation. Thank you so much.